Welcome. I'm sure we'll have some more people funneling in as we get started, but we'll go ahead and kick things off. For any of you who don't know me, actually, how many people have I never talked to, never been in a session that I've given? We have a few? Yeah, we got a few, yeah. So I've been at Microsoft for 15 years now. I've given a lot of presentations on a lot of different things, but for the last 4 years now, I've been working on containers. And as part of that, no good deed goes unpunished. I really look after a lot of our dev strategy and what we're doing for development, both for Windows Server as well as for Windows 10 out of the base division. So today we're going to talk quite a bit about what we are doing in Windows Server as part of version 1709, our first feature release. Most of that is about containers. We do have a few things that I'll throw in that are a little bit tangentially related to containers. Some people asked for an Azure Functions demo, so we've got that added in. This is going to be a pretty demo-heavy session. As interactive as we can make it, that's going to make it even more fun. So for a little bit of context, I'm curious how many people this resonates with. If you're a developer, you spend a lot of time doing the same stuff, debugging applications, fixing an application that is already in production or should be in production, adding a feature to an existing application, maybe fixing the feature that someone else tried to add to the application, and then maybe if you get some free time at the end, you get to try to build something new, and if you're really lucky, you get to build something new with a new tool set or some new code that you're excited about. For the application admin side, for the IT pro, it's kind of the same thing. We're fixing the application, we're redeploying it, we're debugging it, we're troubleshooting problems that someone introduced when they added a feature. We're trying to get some time to think about how we're actually going to deploy a new application, but that's a struggle. The reality is we can't throw all the old apps out. We can't start new. We can't stop adding features to the applications. Right? I think about internally at Microsoft, our absence reporting tool is like from 2003. This thing it's just old. But it works, and people continue to use it because it continues to work. But when we change HR policies, when we give people extra vacation days or a floating holiday, we had to add that feature to the application. We couldn't just say, nah, we'll just not deal with that, it's fine. We can't stop maintaining the app. We can't stop monitoring it, securing it, updating it, patching it, making it accessible, whatever the requirements that come in. But we can make it a lot easier to do these things. We can make it a lot easier to maintain these apps. And we can start to use new tools and new code and new practices as we add those features and as we make those changes to the app. And so we'll talk about some of those patterns today. The session I just gave earlier today with Scott Hunter talked about some of those as well. So if you didn't catch that one, that's a good one to watch as well. But this is the pattern that we're going to talk through and that we've really been kind of prescribing it. So we can containerize our existing apps. Why would we do that? That means we can move the app around. It means we can have portability with it, we can redeploy it, we gain some efficiency out of it, and we gain some reliability in the course of doing that. Then we can start to transform those monolithic apps into more of a microservice architecture. We can do that by adding new code alongside it. So we can add a new .NET Core API alongside of our WCF application, right? And then when we're building new code and new apps, we can use this same pattern to accelerate the development of those. So this is a pattern that we're seeing customers have a lot of success with, and one that we'll be talking through. So to give a little bit of perspective on this, I'm really, really happy to have Dimitri from Fox Media Cloud and Fox Entertainment Group to come up on stage and talk about their journey through this pattern. Dimitri?
Thank you, Taylor. Good afternoon, everyone. As Taylor said, my name is Dimitri Ehrman. I'm the Executive Director of Development and Architecture for the Fox Media Cloud platform. We're part of the Fox Entertainment Group, which is responsible for both television and film distribution of content. And today, I'm going to talk about a program that we went through with Docker, Avanade, and Microsoft in modernizing one of our applications through their MTA POC program, Modernizing Traditional Applications. So a little bit about Fox, and in particular the television distribution side. We have over 1 billion subscribers that leverage our content. That content is leveraged across 500 plus channels worldwide in 170 countries. That's pretty much most of them, if not all. And so as a result, we are really a global company in that arena. As a result, we have a lot of pressure to innovate and consistently deliver on content. So 3 critical pieces in that delivery for us are the time to market, the reliability and elasticity of our infrastructure to be able to scale to traffic as needed. And then one of the other key goals for us internally on the IT side is to improve our continuous integration and deployment pipeline. Now, challenges that arise. Similar to most companies, we have a budget constraint. We can only do so much in a given amount of time, as well as a resource constraint. We only have so many people dedicated to these initiatives across teams, so we can't just easily scale out and do everything we want in a month. So on top of that, we also have architecture constraints. We have some of the monolithic applications that have been running in our data centers for years. It will take a while to re-architect them, rebrand them, put them out there. So we were looking for faster, better ways of doing this. So enter Docker, Avanade, and Microsoft with their Modernizing Traditional Applications POC program. When they approached us at Fox, we were really excited to see how this would work on one of our applications that's built on a .NET stack and deployed into an Azure environment. So we selected one of our applications that I'll introduce in a minute, and our goal was to see, can we reduce the amount of overhead and the amount of spend on maintaining this application, deploying it, modernizing it, improving it, and all those factors, and how quickly can we get into the cloud. So as part of this program, Docker and Avanade and Microsoft put together a 4-week plan. First week, we had Docker and Avanade people on site helping us, working collaboratively with my team to implement the migration to the cloud. The other 3 weeks were dedicated to support from a remote location, just to make sure that we were still able to function, deliver, and deploy. So we chose one application, we containerized it, and put it into Azure. End-to-end was the goal, the entire stack of the application itself, and to walk through how do we operationalize it running in Docker Enterprise and in Azure Cloud. So the amazing part of this was we were able to do this in 3 days. The entire process of converting it from our N-tier application into the cloud. So it was important to see how this application would operate on multiple infrastructure layers within Azure, leveraging Docker Enterprise. We wanted to see, does it reduce and eliminate the amount of time that it takes for us to have deployment downtime? And I'll get to that in a second in the next slide. And then we wanted to see how quickly can we improve the application infrastructure. Can we scale it out quickly? Can we add more worker nodes in minutes as opposed to days where on our traditional infrastructure side? And then how does the continuous integration and deployment pipeline work in that environment? And then one of the things that we also didn't have originally was a disaster recovery plan. So it was important for us to see, can we get disaster recovery quickly and easily? So we chose our broadcast affiliate portal. This portal is responsible for distributing promotional content to our affiliates, that's our television stations across the US. So how many of you see promotions during your favorite show that says, Patriots playing Falcons Sunday at noon? It's like a 30-second spot during a commercial. Those are the promotions that we distribute through this portal to different affiliates. They come to our site, they choose which version of the promotion they want, they select it, we download it or stream it to them, and then they air it as part of their commercial time slots that are assigned to it. So, challenges. This application originally took 3 hours to deploy, which was a required maintenance window. We had to go to the business and to our clients and to various groups to request a time slot. We couldn't just deploy whenever we wanted to. We had to make sure there was no critical deliveries. And there was a lot of manual steps involved in the deployment process. As a matter of fact, this bugged me. It bugged me because, and I'll give you the story, I spend a good amount of my day at the office and traveling in LA, back and forth. So I don't get a chance to do some of my financial work until the weekend. And sure enough, every weekend when I sit down to do my paperwork, one of the sites is in a maintenance window. Anybody else run into that? 6-hour, 8-hour maintenance window. I can't live like that. 6-hour to 8-hour maintenance window. And then I look at my stacks that I oversee, and I have 3-hour maintenance windows. It's embarrassing for me as an IT person, as a developer at heart, that I have to wait 3 hours to deploy an app that I know I can get out there in minutes. And then the other problem that bothered me a lot was the fact that we didn't have a disaster recovery plan. We had 2 virtual machines running the entire application in one data center, and that if anything happened there, it would take us probably days, if not weeks, to bring it back online. And we do have backup contingency plans on how to deliver the content if need be, but that's still not a good way of running your business. So more details about the application. It's a multi-tier .NET 3.5 stack with SQL Server 2012. It didn't leverage a lot of CPU on the virtual machines that we had allocated to it. And it also ran alongside probably 5 or 6 different applications that were sharing the same infrastructure. I've seen this plenty of times. You build out beefy VMs, and then you've got more capacity than you need, so you start shoving more applications into them, which isn't the best way to run your business either. And then all of these were built on Windows Server 2012. The application is fronted with an external load balancer that routes the traffic to those 2 VMs. And then 2 instances of the portal application. We added a Redis cache layer to cache the data so that we didn't hit the database as much. We also had an external MS SQL 2012 infrastructure set aside, and we integrate with other services like Okta for identity, and as well as other APIs to consume metadata and other functions. So what were we able to do with the MTA program from Docker, Avanade, and Microsoft was we went from running this application in an on-premise infrastructure on Windows 2012 to converting it to a 2016 instance of the operating system without a single line of code change. We made a few configuration tweaks, and that was it. We containerized it. We put it into Docker Enterprise running on Azure. We took the Redis cache layer, containerized it, put it in there as well. We did a migration of the database to Microsoft SQL running in Azure, and then made a few configuration changes so that we can continue to talk to our authentication and APIs that were running elsewhere. In this process, we went from running on 2 VMs to testing it out with 3 worker nodes in Docker, and then a single manager node for UCP and DTR. We didn't require, it's a part of a POC, we didn't require the full production setup, but we wanted to see, can we quickly scale out? So part of it, the reason of running 3 worker nodes was to see how we can deploy the code without incurring any downtime. And we were able to achieve this really easily within minutes, not a problem. So the 3 worker nodes were really there just for us to test over the 3 to 4 weeks that we ran this POC. The results. So our typical life cycle for this application was a 2-week agile sprint, development test, and then asking our business when is the good opportunity to deploy the code because it was requiring a 3-hour maintenance window. There's no redundancy in the application stack, and when we needed to do security fixes, my team can quickly patch the application, test it, have it all done within hours. But again, we had to ask for a maintenance window because the application required downtime. So that became a problem. If we wanted to also add additional infrastructure, it would take at least a week to provision a virtual machine running Windows, have it attached to the network, and deployed. So those are all problems that we wanted to see solved. After we put the application into Docker Enterprise, we were able to deploy any change to the application, whether it was a security fix, a new feature, configuration change within minutes. Have the nodes cycle through the Docker migration process, and within minutes, the new features were up and running. The redundancy was there because we can have 3 worker nodes, 5 worker nodes, 7 worker nodes, however many nodes we need to run the application. And then we were doing this with an initial continuous integration and deployment pipeline. It wasn't production ready, but it showed us the path to get there. And then where we needed to do a security patch, we saw that we can do that with no downtime. So now it takes minutes for us to scale. The entire process of converting the application was actually just a 3-day process. And actually, one of those days, we were stuck on configuration changes. So it could have been as easily as 2 days. And those config changes were actually communicating with our authentication APIs. So nothing to do with the program itself. So our team, which was skeptical that we can do it this quickly, was actually quite surprised, and pleasantly so, to see that we were able to convert it in 3 days. What's next for Fox? So while we went through this POC process, we are still looking at how we're going to deploy this into our production environment and go through our change management, information security pipeline. But we were so impressed with this that it spun up a whole bunch of conversations around other applications that we can move into Azure Cloud, leveraging Docker Enterprise. And so this POC is still there, still sitting in Azure, waiting for us to figure out our plan, our roadmap, and how we're going to get there. And this was for us, especially for some of the skeptics on our teams, the developers, and even the operations teams who have never seen Docker running before. They were impressed with how quickly we were able to do this and how little effort it took to convert it. And that's our story. Thank you.
Thank you. So thank you very much to Dimitri and to the folks from Docker who helped get Dimitri out here and up on stage. I think that's a pretty good story. And hopefully you do as well. It's actually a story that we're hearing from a lot of customers right now. A lot of our customers are finding that, yeah, it's actually really pretty straightforward to move an app into a container and get it published and running either on-prem or in Azure. How many people saw the demo in Jason Zander's keynote? A few people, none? Yeah. So my director, my boss, walked through the very same kind of similar process that we use in the MTA. So taking a tool called Image to Docker, it's an open source PowerShell module, converting a website that's running on-prem while it's up and running, moving it into a container, running it locally on your machine, and then being able to deploy it into production, right? And we look at that pattern, and this is kind of what it looks like. We take our existing app, we can move it into a container, we can run modern methodologies like CI/CD against it. So now security updates and patches and those kind of things are treated like config changes as opposed to operational poking and prodding. They're recorded, they're monitored, they can roll back, they can roll forward. We can then move the application into more modern infrastructure. We can start taking advantage of cloud, or even on-prem, we can start taking advantage of cloud-like deployments, right? And we now have a path to start using modern microservice architectures alongside that application. So let's take a little bit of time and let's just go through kind of what is a container, how do they operate, how do we use them, and spend a little time just playing around. So of course I have to sign back in. I took a flight before I came down here of Windows 10 that has a bug with Windows Hello, so I have to put in my PIN. So this is actually my desktop machine. I'm going to connect to one of my other desktops back in Redmond, or hopefully connect back to my desktop in Redmond. And we're actually going to walk through just the process of running a container, building a container image, and kind of how the internals of all of this work. That machine doesn't come up. We've got another one here. Try this guy. All right, we'll see if that one comes up in the background. So this is actually a VM in Azure. So all I have to do to run a container is I can just simply say docker run and the name of the container image. Actually, I want to do IT so I get an interactive console. So the container image we're going to start with is Microsoft, Windows. Actually, let's do Nano Server. A little faster to start up. Nano Server, and then the command I want it to run, which is just a command prompt. So we're now starting up a container. So this container is now getting started up in the background. And while it's doing that, I'm going to open up Task Manager. This is running with a shared kernel. So this means that the user mode of this container is running in its own isolated world, but the container itself, or the kernel, is shared. And I can look at this by selecting this Job Object tab in Task Manager. And I can see that there's all these ones with Job Object 192. And if I start up another process in this container, so if I do something like cmd/k. So I've now run a second command prompt in there. We can see that there's now two command processors running. If I exit one of them, one goes away. So that's running in its own container, but it's fully isolated away. So if I go to Windows System 32, System 32, this is its own copy of System 32. And I can do stuff like del star. And I'll get access denied because I'm not running as an admin, or I don't have rights to do that. But I can also do something like or echo foo to bar.txt. So I've just made a file name bar in C:\Windows. But if I look at the host and go to C:\Windows, Windows, there will be no bar.txt in here, right? Because that is in the container. The container has its own file system. It also has its own registry, right? It's fully isolated away. If I exit this container and start up another one, I will get a clean container. I'm going to get it from a clean starting point. So if I go to Windows, that file's gone. It's been lost to the world, right? Now, that's kind of neat, but like, how do I actually do something useful like install an application or use this container for a longer period of time? Well, let's create a couple files in here. We'll say echo hello to hi.txt. Let's just say that that represented an application being installed in our container, right? So I'm going to exit this container, and again, that guy is gone. But if I do a docker ps -a, I can see all the containers that I've run recently. And that one that exited 40 seconds ago with this ID, that's the container that I made that change in. So I can do two interesting things now. If I wanted to, I could do a docker restart on that container, and I could start it back up again. And I could do a docker exec, so I can run a command inside of it with that container's ID. And I'm back in that container, and sure enough, our hi file is there, right? So I could rerun it. But more interestingly, I could actually create an image out of it. And I can do that by saying something like docker commit. What docker commit does is it takes that container ID and, oh, I've got to stop the container first. So we'll say docker stop, and then we'll do docker commit. It takes all of the changes that were made from running that container, and it squirrels them away into a new file. And if I do a docker images now, I can actually see this weird image ID that doesn't have a name with it. That's the one I just committed. So if I run a new container from that image ID, which I could do just simply by saying docker run again. So I'll use the ID as opposed to the name and cmd. Sure enough, our hi.txt is still there, right? Because I'm running it from an image. Now I could run 1,000 of them from that image if I wanted to. I could run 10 of them. I can also start to do things like shipping that image around. And we'll talk about how we actually do that in a minute. But what's more powerful is when we can actually use automation around that. And we do that by virtue of what we call a Docker file. So if I had to go in every time and say, okay, I'm going to install a new version of the app, and I'm going to do that by doing a Docker run and installing the app and doing a commit, that's not all that much more efficient than what I'm doing with a VM. But if I can do it with automation like a Docker file, it really is. So let's see if this other machine's up, because I've got stuff cached in it. And it'll make it a little faster. Try to reconnect to it. All right, well, we'll just do it by hand. That's unfortunate. So make directory foo. And inside of foo, we'll just make, oh, there we go. To get lucky. Maybe. So I actually brought a demo machine physically here, and it blew up on the plane somewhere along the way. So we're into redundancy land. And apparently Redmond is not very fast. All right, let's go back to it. We'll go back to Azure. Maybe. All right, we'll see if this reconnects. I'll talk through it. So we can use a Docker file, and a Docker file allows us to say, start from this image. So our first line of a Docker file says from Microsoft Nano Server, for example. Like, that's what we started with before. All right, here we go. We'll make one. Notepad, Dockerfile. So we'll say from Microsoft Nano Server. All right, so that's saying I'm going to start from that image. That's the image I'm going to use as my basis. And I want to run a command in there. So I'm going to run a command, echo hi to foo, right? Very similar to what I just did a few moments ago, right? Now I have to move Dockerfile to Dockerfile. So now I can say docker build, and we'll give it a name this time, hi, and I can point it at that file. Now what it's doing is it's actually running a container. So it says, see, running A, D, E, whatever. That's the container it's using to run that command inside of it. So it's just run that command, and now if I do a docker images, I can see hi. That is that container image I just created. And if I do a docker run hi, sure enough, we've got foo, right? We've got the file I just created in it. Now the other cool thing about Docker files is that they're smart. So if I go to this Docker file and I add another line to it, so we'll take this line, we'll add one more to it, and we'll say hi to bar, right? You can tell my favorite samples are foo and bar. If I say docker build again, it skipped this first one. It said, hey, from cache. It did that because it knew that it already had a container that had that command run on it from that basis. It knew that that was not going to be a new container layer. It didn't need to run that again. It could just start from the existing point in time and then add that next command on top of it. So if we do a docker images, we'll see we've got hi with a new image ID. The new image ID is an additive image on top of it. And again, if we went and ran docker run hi and did a directory listing, sure enough, we've got foo and bar both listed in there, right? So this is the basis of how we go about running containers, right? Now this whole time we've been talking about what we call Windows Server containers. They're shared kernel based container. Let's see if this guy's a little faster. I'd love to show you Hyper-V isolated containers and the difference. All right, there we go. So on Windows 10, by default, we run Hyper-V isolated containers. That means we're actually running it inside of a little micro VM. So if I say docker run, same command that we did before, I'll do it nano Microsoft / nano server, CMD. So we're actually starting up a special little VM in the background to run this container in. And it started up that fast. But if I go and do the same thing we did before, and I look at Task Manager, if we can get Task Manager up, and if we look at the processes that are running there, assuming it comes up, we won't see any of the processes that are running in this container this time. So if I go to details now, boy, this is terrible. I wouldn't see any of those processes because they're running inside of a little special VM. Why do we do that? Well, there's a couple reasons that we do. We certainly do it for isolation. So if we want to run a container that's running third-party code that is not trusted in Azure, for example, which is where we built this for originally, we run it to run inside of an isolation boundary. On Windows 10, we want to do it because we want to run in exactly the same configuration we're going to run in production. We want to run with the same kernel policies. We want to run with the same server install. We want to run everything as close to what we're going to do in production as possible. So we always run all of our containers on Windows 10 inside of Hyper-V isolation. So we'll go back to slides here for a minute. So this is kind of what that ends up looking like. So we talked about Windows Server containers. That's the guys on the left there. So they're running with a shared kernel. Each one of them basically runs in its own user mode. And then on the right, we have Hyper-V isolation. So we're running a Windows Server VM, effectively, with a container inside of it. But it's a special VM. It has special properties. It shares memory. It has high density. We actually use a technology called cloning to start these up faster. There's a whole bunch of things we can do with that special VM because all it's designed to do is to run a container, okay? So it's a pretty special little trick that we get to play. And that has given us a lot of power. That's given us a lot of opportunities to optimize the way that we actually run stuff. So I'm trying to reconnect to a different Wi-Fi, and we'll see if that helps connect back to that machine a little faster. So there's a couple of tools that we can use as we think about how to build these images. Image to Docker being certainly one of the ones that I use a lot. We talked about it in the demo. So what image to Docker does is it takes an existing machine, you run this convert to Dockerfile command against it, and give it some information about what you want to convert, and it will give you a Docker file. Now this is a more complex version of that Docker file we talked about earlier. In this case, we're saying from ASP.NET, based on Windows Server Core, run some PowerShell. That PowerShell removes a website, it adds another website, it copies some files in. The end result of running this through a Docker build is you're going to get a website that looks exactly like the one that was running on that machine. Now, because I can run this all on my desktop, I can go test that. I can run the convert to Dockerfile command. I can point it at a web server. I can get a container image out of it. I can run it on my local machine. If it works the way I expect it to, I can put it in production. If it doesn't, I can go to the next web server. Right? I can actually just literally automate and do trial and error if I wanted to. Right? This is all open source PowerShell module. It's on Docker, Docker Community Tools. I've got a link to it in a second here. You can run it against WIM files. You can run it against VHD. You can run it against a VHDX. You can run it against a live server. It would be super easy to add support for VMDK or any other format to it. Because really all it's doing is groveling through the file system, picking up those elements and artifacts, and creating container images out of it. It looks through all the roles and features that are on the machine. It also looks at what programs have been installed to try to find things to pick up. These are the artifacts that it has support for today. So IIS, HTTP, ASP.NET, SQL instances. I use this for SQL servers all the time. So I can take a production SQL server and make a container image out of it that I can then use in development that has exactly the same database files that production would have. So now all the developers can have an exact copy of production. So here's some pointers to go get it. The other really cool tool that we have is Visual Studio. So we've added a bunch of container support into Visual Studio. We can now just right-click on an existing Visual Studio project and say Add Container Support. And it will scaffold in all the things necessary to build and run a container. And let's give this one more try. Let's see if we can actually make everything happy here. So if I open up Visual Studio, we'll walk through the whole kind of experience here. So I can go File, I can add a new project. Let's say I'm just going to use an ASP.NET web application. So this is going to be a typical like ASP.NET 4.7 web form project, right? We'll let that create. So I will say, sadly, the presenter Wi-Fi is slower than the attendee Wi-Fi, so we use the attendee one. All right, so now all I have to do is I can say add, and I can say Docker support. What this does is it just adds in those Docker files into the existing application. So you can now see that we've got a Docker file here. And this Docker file, very similar to what we had before, it says from ASP.NET, and it uses some additional commands called arg that we won't go into today, but they're documented, you can read about them, and copies in the source file. The other thing that it does, though, is it adds what's called a Docker Compose file, and Callie will talk about this a little bit later. Docker Compose is a way for us to describe multiple containers as an application. Because a web server is not usually an application by itself. How many people have just a web server and that's the only, that is the app, it's just a website? No, it's usually website, maybe a database, usually a middle tier and a database, right? This would allow us to describe multiple pieces to that. In fact, if we were to go over here and say to the same solution, add a new project, and let's say we were going to do this pattern of using new with old, so we'll add a .NET Core web application. And in fact, we can just say enable Docker support right from there. We'll make it a web API and hit OK. What will happen is our compose file will automatically add in the new .NET Core web API. So now if I hit F5, it will actually deploy two containers, one for the web app and one for the ASP.NET Core API. Right? So this is that pattern of starting to use the new programming methodology with the existing app. Right? If I had had a whole WCF app, I could have started using those together. Right? So these are some of the tools that we have available for actually building container images. So what do we do when we're done building them? Well, when we're done building a container image, we've got to have somewhere to store it. We call those registries. So a container registry is a place where we can stack all of our containers up. We can have versions of them. We can deploy them from there. We can synchronize. We can do all sorts of interesting things from a container registry. Now, the one that's the most famous is the Docker Hub. The Docker Hub has millions of container images that are available just to download. So Microsoft actually publishes, last time I counted, 75 different images to the Docker Hub. There are things like Server Core and Nano Server, but also SQL Server, .NET, IIS, ASP.NET, WCF, a whole swath of container images that are just ready to go, along with the Docker files that actually built it. So you can actually go see, how did that container image get built? Why would you want to know that? Well, maybe you're going to do a security audit, and you need to know exactly how this application was built line by line from the base. You can construct that by just looking at the Docker files that were built. And in fact, the container images even carry along the information about what command was used to create that layer. So there's a great opportunity to introspect a lot of this stuff. So let's go back and we'll take a look at the container images and how we use them. So again, we're in a container right now, so I got to exit that guy. So if I do Docker images, we can see the images that are available. So this machine has a couple images already installed on it. It has ASP.NET, it has IIS, it has Server Core, it has Nano Server, and then it has two of our insider builds. So these are the new versions of Server Core and Nano Server. One thing I'll call out before we move forward, this was what we had for Server 2016. Server Core was 10 gig. It's a pretty big image. Typically container images are measured in megs. This is what we have starting with 1709. That was the amount of difference we could make in 3 months of engineering on the container image size. So we think that's a pretty big deal. The result of that is that a poll time went from, where's my notes here? The poll time went from 6 minutes on average down to 2 minutes and 40 seconds. So it over halved the time it took to download Server Core. Nano Server went on a really big diet. We took it down from about a gig down to 200 meg on disk. On poll time, it went from 49 seconds to 9 seconds. Pretty big difference. And it went from almost 400 megs down to 80 megs in compressed size. So pretty big difference. So let's go take a look at another set of images. Let's go to hub.docker.com. So here's where we can go and we can search for different images. So let's search for something like Redis. So here's a whole bunch of images. This is a Redis image. Now, a lot of these images, in fact this one, happen to be Linux. This happens to be a Linux image, which until recently I meant I couldn't easily run it on Windows 10 without running it into VM and doing some additional work. But we have been working really hard to add support for running Linux containers natively on Windows Server. So I can go over in here and say docker pull, actually I don't even have to do that, I can just paste in the command I just had, docker pull Redis. So I am now pulling down a Redis container built on Linux using full regular Linux images, a Linux kernel and everything. And as soon as it's done downloading, so it's pulling down the various layers that built this image, I can now say docker run, and I'll do an IT Redis. We'll just run sh in there so we can actually interact with it. And we are in a Linux container that has Redis installed in it. Yeah. Oh, I'm in the Redis image, that's why. This is actually running Linux, and you can see I am not as well versed at Linux as I am at Windows. But we're actually running a full Linux image now, and we've just pulled that down from the Docker Hub. Now, what's kind of nice about that is that if I'm a developer, let's close this window, I can now use Windows and Linux images together, which is pretty handy. Right? And so that's an example of pulling one down from a registry. Let's look at pushing one up. So let me go back over to that other machine that has an image already. This was all supposed to be from one machine until we had our Wi-Fi issues. So if I wanted to push an image up, again, this is the one that I have high on, I can say docker tag, and I'm going to tag that high image with, docker tag t, the registry name. So this is Azure Container Registry that I'm using for this demo, and the image name. Oops. Oh, wrong order. I always get this order backward. So I've now tagged that with this image name, and that's important because that's what's going to give me the ability to tell it where to go when I want to push it. So now if I do a docker push that image name, it's now pushing that up to an Azure Container Registry. So if I go look at our Azure Container Registry in the portal, so I'll go to MS Portal Azure, we'll actually see that container image residing up in the Azure portal. So this is the way I have mine set up. I use resource groups to manage everything. So I'll go to my demo resource group. We can see a bunch of VMs. We can see this container registry. And I can go to repositories. And there's the image that we pushed up there and the latest tag for it. And I can actually drill in and see more information about this container image if I wanted to, right? So now what we've done is we've taken an image down from Docker Hub, and we've pushed an image up to the Azure Container Registry. That would allow us to now take that image and go push it down to another machine. I can go to any other machine and pull that image down and run it exactly the same way that it was just running on that machine, right? So I'll go through these slides pretty quick, but these are some information about the Azure Container Registry. We've got, it's going to be GA with managed registries in October. Geo-replication is now in preview, so this allows us to actually replicate all those images all the way around the world. So if you push an image into it, you can enable replication, and it will replicate it to all over the world. The cost for it, the basic plan is $5 a month. There's a standard and then a premium option available of Azure Container Registries. And again, a little more on geo-replication. The other option that I would be looking at would be Docker Hub. You can also get private registries there if you want to have a registry available for your team. Or, and we'll talk about this in Docker Enterprise Edition a little more, what Dimitri's team is using would be Docker Enterprise Edition, which has its own private registries. So I'm going to really quickly do a quick demo of Azure Container Instances, and then I'm going to get into orchestration. So Azure Container Instances allows us to just run a container natively in Azure. And I can simply do that by just saying run instance straight from the Azure portal. So I can just give this a name like my container. It takes the image name. It takes what kind of image it is, Windows or Linux. And of course, what resource group I want it to be run in. So for the sake of this, go down and find my demo one. Boom, number of cores, port, and OK. So it'll then validate that, and it'll actually run a container based on that image. Just that easy. This isn't really generally what we use for running production applications, though. It's great for just running a container, and it's really infrastructure. What we want to do is we want to have some sort of management plan on top of that. Because, again, it's not much use if we're having to go back and click through a portal every time we want to update a version. We want some sort of centralized management of that. And to talk about that, I'm going to bring Callie up to talk a little bit about orchestration. Now, orchestration is basically the process of managing multiple containers together, right? So we now manage them as an application.
Thanks. Thank you. Okay, yeah. So as Taylor was mentioning, a lot of what we've already talked about today is about how to run your containers within a single host. So maybe that's your dev machine, maybe that's a server, but either way, you're thinking about one host. You can use like tools, all the tools we've seen today in Docker Compose, which I'll talk about a little bit more, to define an application and your container images and applications within a single host. So maybe your application has a front end and a back end. It doesn't have to just be one container. You can start thinking about your container within one host. But if you want to start thinking about containers for deployment in a cluster across multiple hosts, you need to start thinking about orchestration. So today I'll give you kind of the intuition for what orchestration is, and then talk about Docker Swarm, which is one orchestration solution. I'll talk about that just to give you the intuition for the kinds of things that are involved with orchestration, and a lot of the concepts that I'll cover will actually apply to all orchestrators. How many of you are familiar with orchestration, or if you've used an orchestrator like Docker Swarm or Kubernetes before? Okay, cool, gives me a little bit of an idea. Okay, so I want to talk about the tools that you need to run containers in general, right? So whether you're thinking about your application running on a single host, or whether you're thinking about running your application across multiple hosts in a production environment and on a cluster, the first thing you obviously need is your container host and your runtime. So that's been kind of implied here, right, is you need some kind of container host that will support containers. We've seen Windows Server be the host today for both Windows Server images and for Linux images. But either way, that's the first kind of ingredient you need. Right, and Windows and Linux are two popular runtimes. So Windows Server, you could also run on Linux. The second thing you need, which we've talked about a lot today, is a management layer. So the management layer we've used as the example today is Docker. All the commands we've been running is Docker. That's your management layer so that you can so it makes it easy to create container images, to run containers, to commit containers to new images, push and pull to registries, everything we've seen today. That's been used with a management layer. And in this case, we've been using Docker. There's also LXC, but Docker is definitely the dominating, most popular management layer today. So where we see this picture start to look a little different is orchestration. So orchestration, again, is the tool that you need to start thinking about your application in the production environment across a cluster. So here's some examples of orchestrators. Docker Swarm is the one I'll be talking about today. This is Docker's built-in orchestrator. It's built into Docker Enterprise Edition. You can use it with Docker CE as well. And then Kubernetes is a big one. And then another is Service Fabric. Service Fabric is Microsoft's first-party orchestrator. It's actually what Azure uses. And then OpenShift by Red Hat is another. Okay, so all of these, I want to talk about the basic things that all of them provide. As you went and dived into these, if you're going to start learning about each of them, you'd start to identify differences between them. But what I really want to key in on is the things that they all have in common, right? So that you can have the intuition to understand any of them. The differences is just how they do these things. So the first thing that an orchestrator needs, the thing that makes an orchestrator, is for it to define some kind of model that you can use to declare your application in a cluster environment, right? So we have a way to think about, as we've seen today, we think about images, we think about containers. Docker Compose on a single host allows us to start thinking about services. In the demo that Taylor just did, he had the web application one that was bringing the concept of a service in, right? But then we kind of need to extend those kinds of abstractions in a multi-host environment to suit that environment. So that's the first thing that an orchestrator provides, is a way to think about your applications in that environment. For example, with Docker Swarm uses services. Kubernetes, a big piece of their abstraction is pods. Okay, so a second thing that all orchestrators will provide is some kind of desired state reconciliation. So you've defined your application and what it means to run it on your cluster. But then a part of the orchestrator's job is to make sure that the application's always running to match that state that you've defined. Right? So your nodes might go down, maybe just a single container task or multiple tasks goes down. Lots of different things can happen where your cluster at any given moment might not match the desired state that you've defined. And part of the orchestrator's job is to say, hey, does the application look like how you've defined it at any given moment? If it doesn't, then it needs to solve that. So for example, think about if you had like a 4-node cluster, for example. Maybe it was running 40 containers, maybe they're multiple services, whatever, but 4 nodes, about 40 containers, maybe 10 containers each. If one of those nodes goes down, then 10 of your containers are now down. So the orchestrator will say, okay, a node's down, 10 containers are gone, and it'll schedule those 10 across the 3 remaining to make sure your application is still available as you expect. Okay, another thing is at first you might run your application and it just, for each of your services, it might be backed by just one container instance. So, but then you might want to scale that out, right? So maybe demand for, or maybe it's more than one, but demand for your application is going to need more instances for your service. So another thing that orchestrators provide is scaling. So the ability to run a service and scale it up. I'll show this later. So another thing here is high reliability. So aside from making sure the state of your application matches what you've defined, the orchestrator also will have mechanisms to make sure that your whole cluster won't go down. So an implication here is that each orchestrator needs some kind of master node or some kind of master controller entity, whether it's some of the nodes themselves or some other kind of entity, to keep track of what's going on across your cluster. But what happens if that itself goes down, right? Who's going to be around to make sure that your state matches if the controller itself is gone? That's where high reliability comes in. That's an example where, for example, in Docker Swarm, we use master nodes. So for high reliability, you might want multiple master nodes. So these are the main things that all orchestrators will certainly provide and have mechanisms for. Some orchestrators will also start adding additional capabilities, like health monitoring and security, and so on. Okay, so again, I'm going to be focusing today on Docker Swarm, but I just want to use that as intuition. And there's 2 reasons that I really want to emphasize that although I am talking about Docker Swarm, the concepts apply to other orchestrators. The first reason is just for you and your knowledge. I want you to know that these kinds of concepts do scale. And the second thing is from the Windows Microsoft perspective, our goal is to make Windows the best container host, right? So I work on I skipped this, but I work on the core networking team at Windows, at Microsoft. So it's my job to work on Windows and make sure and to connect containers to the network, right? So when we think about orchestration on my team, it's all about it's the networking components. And so across Docker Swarm and other orchestrators as well, we have central components inside Windows that handle networking. So really the way we think about it is just to expose those capabilities up so that any orchestrator can use them. Okay, so let's really dive into Swarm. So when you think about using Docker Swarm, or Swarm mode, it's a workflow with kind of 3 parts. So the first part is you have all of your nodes. They're connected to the physical network, so they can talk to each other. And you'll use 2 really simple commands to connect them and say, hey, you're all working together in a Swarm cluster. The first is Docker Swarm init. So wherever you run Docker Swarm init, you can run it on one or multiple of your hosts. Those hosts are now master node hosts. So it's their job to keep track of the state of the swarm and so on. And then you can run Docker Swarm join with a special security token to add additional nodes to your cluster as well. So once you've done that, each of your nodes has Docker installed. But what's happened is the Docker engine on each of them after you run these commands are working together in Swarm mode, right? Okay, so then the third piece here is actually deploying your app on the cluster now that it's set up. And that's where I'll talk a little bit more about Docker Swarm. And if you do use it, you can do this with manual steps as well, but if you do use Docker Compose, it's this simple single command, Docker stack deploy. Okay, so let's take a look. Okay, so here's a diagram of my cluster that I have here for my demo. It's three machines, 2 Windows Server Core hosts, and 1 Linux host. As Taylor mentioned, so let me back up. The application that I'm using for my demo has a Linux backend. It's running a Redis Alpine image. And then the front end is Windows-based. So the way I've decided to set this up is to have one of my actual physical container hosts be a Linux host. Of course, you don't have to now with the Linux able to run natively on Windows. Okay, so again, the Docker Swarm init is the first command you'll run to say, hey, this first host in my cluster, I want you to be a manager node. The next command is the Docker Swarm join, Once I run that, I'll add my second host, and then my third. And then all three of them are running together in this swarm. Okay, so let's look at the application now, and the Docker compose file that I wrote for this simple application. I'll show it running shortly. So this on the left here is a Docker file. It's an example of a Docker file. So for my application, the front end is a simple web service running based on an IIS web server image. So in the Docker file here, I'm defining that with that service with the web syntax. And then I have a similar service defined. This is my backend service. It's a database service. Now, I also need to define the images in my compose file for each of these services. So this line here defines the image for my web service, and then the next is my image for my backend database service. Now, of course, these need to talk to each other. So how do you do that across a cluster? And this is where my team developed the overlay network driver. So the overlay network driver is the underlying driver that Docker uses when you create an overlay network, which is just the type of network that you need to have multiple services running across a cluster to talk to each other. So in this case, my overlay network, I just called it HelloNet. And then this syntax here for each of the services is how I've defined in my compose file that these services should use the HelloNet overlay network to talk to each other. Okay. So now let's see this running. So I was too nervous to try to connect back to my servers in Redmond, so I just have videos, but okay. So the first thing I'll show here is my, here, I want to be a bit more manual here. Okay. So the first thing I wanted to show here is my application's already set up. So I skipped the Docker swarm init, the Docker join commands, but I want to show you what it looks like. Here, I'm RDP'd into swarm host 1, which is my first node of the 3 in my cluster. The first thing I want to show you is that from this manager node, I can see which nodes are in my cluster. Here you can see the three nodes. They're all active. There we go. And then I'll also show you the network that I created. So there's the HelloNet network that I showed in the diagram. And then the services are also created already. So I have the Hello DB service, or the DB service, I changed the name, it looks like, and then the web service. They're each right now just running one replica each, which means that they're just running one container instance each. So now I'm going into a browser here and I'm going to view the web app that I have. I'll talk a little bit more about the addressing there in the swarm host with the port 8000. But all this app does is it counts how many times the web front end has pinged the database backend. So there's just a counter in the Redis database counting how many times it does that. Super simple. And then at the bottom here, I'm showing the container ID and IP for the specific container that answered this request. So if I go back into my master node and I do docker ps, I can see that the ID for my container running on my cluster matches that ID there. So my app's super simple, just a way to see what's going on here. Okay, so now let's talk about scaling. Obviously, the whole point in talking about orchestration is to talk about your application being scaled out, right? And so what good is one replica for us? So I want to change my picture up a little bit here. This kind of gets a little bit tedious, so I want to simplify it. The overlay network's still there, but I want to simplify here and just look at the service. So this is the command that you use to scale a service using Docker. So it's just Docker service scale, web is 3. 3 is the number of replicas or containers that I want to run from my web service now. We can see this back in the demo as well. Okay, so I'll just run Docker service list. So you can see that right now they're running one replica each or one container each. Now I'll scale my web service to 3 instances. It just takes a moment here. Okay, and then I can run Docker service ls again, so I'm just listing my services. And I can see now that the web service, it was running 1 before, but now it's running 3 replicas. So it's running 3 containers. And those are across my 2 Windows hosts out of the 3 in my cluster. Okay, and you can see now, so you'll see that I'm doing this because my ID and IP will switch now as I refresh, and my app does this. It's still talking to the same single container on the back end, but the front end containers that are actually servicing my requests are changing back and forth. Yep. Okay, so something kind of interesting here is port publishing. We saw that a little bit in one of Taylor's demos in the Azure portal. You could choose a port for your container when you ran it. So I'll talk about what that means on a service scale. So again, I just want to simplify my picture a little bit here. Replace the nodes of the names of my nodes with some IP addresses or some host names. Okay, so when we talk about service publishing, the basic idea is we want just as I've been doing in the demo here, we want to be able to go to a browser and go back and talk to the application running inside in the swarm. So another way to put that is resources outside the swarm may need accessibility into services running on the cluster, right? So for Swarm specifically, there's two ways to do publishing for services. I'll talk about them both because they kind of need each other for context. So the first is host mode publishing. This has been supported on Windows since we supported Swarm mode since February. And the second is routing mesh, which is the one I'm actually using in my demo, and it's new to Windows. It's the default for Docker. And so the main take home that I want you to take, I'll explain both of these, but the main difference between them is that host mode is definitely more optimal for production. It's about performance and having control over your network and how all of the requests into your services are actually being load balanced and so on. Ingress routing mesh does a lot of the work for you, so it's really optimal for developer scenarios. It does a lot of load balancing for you and so on. I'll show you that. Okay, so let's talk about host mode. So host mode service publishing, super simple. Basically, all your containers, wherever they are running on your cluster, they each get their own publishing information on the host where they're running. So in my picture here, you can see that if Web 1 and Web 2 were running on my first host, that's where they're going to be published. There's going to be a mapping from a container port to a host port there. And then Web 3 is running on my second host, so that's where it's going to be published. Those are the only places they're going to be published. And so if I want to access them in this scenario, I can use like these three different approaches. So I can use my Swarm host 1 with 2 different ports, or I can access the third from the second Windows host. So what this implies here is that if, from the perspective of a resource outside of your cluster, like the web browser, you have to know where your tasks are running and you have to target them explicitly, right? Obviously, this isn't how you would really do it. You would really set up a load balancer. And you would configure that load balancer with all of the information for where all of your containers are running. And the load balancer would do this for you, right? But the implication here is that if something fails or if something changes on your cluster, host mode just leaves it up to you to configure that, which again, it can be optimal for production scenarios, but isn't always optimal for developer scenarios. So again, if a container goes down, then now you can still access the first 2, but the third you can't. So that's a problem. But you obviously just need to set up automation to handle that. Okay, now for routing mesh for comparison. So routing mesh is based on the concept of an ingress network. So basically, okay, let me show you this. So the net effect of routing mesh is that instead of having each of your tasks published to the unique port where they're running, you have them published to one port on every single node, even the nodes where there's no task currently scheduled. So in my demo here, there's never going to be my Windows container scheduled on my Linux node. That's just how I have it set up. But I can still access my web service published from that node because all of them are published on port 8000 of each of the nodes, right? Okay, so in this case, you can still set up a load balancer, and you should. But now all your load balancer has to know is the IP addresses for each of your nodes. And that's all it has to track. And so what the implication here is this time, if a container fails, everything will still work. And behind the scenes, Swarm will notice that that failed. It will schedule it somewhere else, and your load balancer will be fine. You didn't have to do anything. Okay, how am I doing on time? Okay, okay, cool. Well, I was here, let's see. I want to show you what this looks like in the browser. Well, figure out how to switch through my video. Okay, so that's swarm mode. So again, I want to return back to the idea that these basics of swarm mode that I've shown you, they're the same kind of constants that you'll see across all the orchestrators. So if you're getting into container orchestration, these are the same kinds of services that an orchestrator will provide for you. Okay, and once again, our goal is to make Windows the best container platform, so we don't choose one of these orchestrators, right? Like we don't prefer one of them. But what we do want to do is make sure that Windows has the basic setup that it needs to support all of them. So these are some of the things, for example, that my team we on the networking team had to do to support what we do today with Docker Swarm, Service Fabric, Kubernetes. We had to build network drivers, we had to build virtual network components, we had to support the abstractions, make sure those were being supported all the way through the Windows platform. Okay, thank you. Thanks.
All right. So a little bit more detail on some of the orchestrators. So the way you would generally buy or use swarm mode in production would be through Docker Enterprise Edition. So this supports both Windows, Linux, and mainframes. It can run on-prem, it can run in the cloud, it can run in a hybrid configuration. It's self-healing, has rolling updates, health checks, end-to-end security, LDAP. It's got all the things that you would generally expect to see in an enterprise application. A couple links for where you can go get it and play around with it. The other option would be Kubernetes, and I'll take a minute and a second here and give a quick demo of Kubernetes. This has preview support for Windows Server containers now. We're looking towards having that be generally available probably a little later this year. The control plane runs on Linux nodes. So you run the actual control plane on Linux nodes. It can run as a Linux container. And then the actual engine, what they call the kubelet and the kube proxy, run on Windows or Linux nodes. An interesting thing about Kubernetes is that all of the networking in Kubernetes is done at layer 3. And when you think about containers in these modern architectures, that's really where the network is running anyway. It's running at IP layers, not at layer 2. Today we have a limitation, or we had a limitation of only one container per pod for Windows. Pods is a construct in Kubernetes where you group containers together. And in Linux, you can run as many containers in a pod as you want. We had a limitation of one container per pod. That limitation is being removed in version 1709 for the shared kernel containers, for Windows Server containers. And we're working on removing that limitation for Hyper-V containers or Hyper-V isolated containers in either the spring or maybe next fall, depending on how far we can get, how quickly. The easiest way to play with this, and I'll show you an example of it in a second, is to use the Azure Container Service. And so actually, let's just go on over to that. We'll see if the network gods are a little more favorable. So this is just my local host, and I'm using the Bash subsystem, the Windows subsystem for Linux, which is another thing that my team works on and owns. And I've already got a instance of Kubernetes up and running in the Azure Container Service. So all I'm doing is I'm using ACS, the Azure Container Service, Kubernetes browse. I'm giving it the group and the name of my Kubernetes instance. And so what this is actually doing is it's creating a local loopback tunnel through WSL, through the Windows subsystem, and publishing a port that I can go look at on my machine. So it's a nice secure SSH tunnel all the way into Azure. I'm actually not publishing any of this out publicly. And this is what a Kubernetes UI would look like, right? So we've got a couple deployments and containers running on here. So I've got one called test. I can go in and look at it. I can look at the logs. So this is all the things that have been spit out from it. So we can see it's got some errors. I would probably want to go look into those and figure out what's going on. I could go do that through straight from the Kubernetes UI, or I could go look at that through a command line. So let's say I wanted to actually create a new application. I can really do that as easily as just saying, let's say, hello, Ignite, and the container image that I want. So I'll say Microsoft IAS Nano Server, and the number of instances I want, and then whether I want it to be internal or externally accessible. So I'll say external, and I can say I want it to be on port 8080, let's do 8081, and what port I want it internally, and I can do that for many ports as I want, and hit deploy. And Kubernetes will now go off and deploy that container on a node, right? Now, another interesting thing I can do from that is, I did that all from a UI, but I can go in and view the deployment. So this is the version of kind of Compose that Kubernetes uses. It's a YAML file that defined all the things that were part of that deployment. So I could go pull this off, and I could save it somewhere, and I could use that as a deployment artifact. In fact, I've even got one on my machine here. So if I do ls, there's one called IIS-JSON. If I open that in code, I would see, or I'll see the description in JSON format for deploying this thing to Kubernetes. So here's the spec. I'm naming it IIS. Here's the containers, the publishing ports, and how it's going to get published out. Now, obviously, we're doing this pretty quickly. This isn't meant to say, here's how you can do everything. What I would encourage you to do is to go play with this stuff. I sped up that Kubernetes cluster in about 20 minutes in Azure. I played around with it. When I'm done with it, I'll throw it away. I'll set up another one. It's not a huge amount of time, but you're gaining some insight into the ways that these different orchestrators work. What I'll often advise, and as we talk about the next orchestrator as well, go play with a couple of the orchestrators, find out what's common across them, and find out what's different. The differences matter, because that's the area where you're either going to love what they're doing and kind of associate and say, yeah, that's the way I want to operate, or the areas where you're going to get into trouble because they're going to specialize, right? So Service Fabric is the other one that we talked about, has support for Windows Server containers, Hyper-V containers, now Linux as well. Image activation, it has what we call volume drivers, which is a way for us to publish data back into a container. Networking modes, resource governance. They've got a whole bunch of sessions here. As Callie mentioned, a lot of the orchestrators are doing exactly the same thing, or the same kind of task, they just do it in a different way. So I would recommend you take a look at a couple of the different ones. And with 2 minutes left, I have one more thing I wanted to demo, which is Azure Functions runtime. How many people have ever used Azure Functions? A couple of people. Azure Functions, it's pretty cool. It's stateless or serverless computing. So you basically have a set of code, you configure and say, on a certain event or on a certain trigger, run this code. And traditionally, it's only been available in Azure or in AWS's, their version called Lambda, or other clouds. What Azure Functions Runtime does is it allows us to bring that on-prem. And it does it with the exact same model, same portal, same publishing experience, but we can run it on-prem. So let me just show this. This is a preview. We're going to be adding a new version of it later this year with some additional features. And our goal is to continue to iterate on it and add more stuff to it. So this is the Azure Functions runtime. It's running on my local machine, and I can go in and say, hello, and create a new Functions app. And I can go into that function and add a new event. I'll use a timer trigger. So I've created a C# timer trigger, and we'll set that to go every 5 seconds. Oops, where did I get something wrong here? Of course, I messed up the trigger, so we'll just use the one that's already running. So I've gone ahead and created one ahead of time. And all this function has to do is it just runs a container in the background. So if I do a Docker PS on this machine, we can see these are the containers that are actually running those functions. So it'll run automatically in that container, just the same way it does in Azure, but it's using our container infrastructure locally to provide that facility. So it's the exact same publishing experience, same everything that the developers are using in Azure, but running on-prem. And it's free. There's no additional cost to it. So a pretty cool capability. So with that, we have 12 seconds left. So we ended just on time. Please submit feedback. Our apologies for network delays. A bunch of great sessions this week. I've highlighted a number of them. These slides are available, so I'll go back to the beginning and show you the link to the slides. But please do take a look at the earlier sessions or the sessions later in the week. And I hope you all have a great conference.